In this problems class, we'll try to solve two exercises. The first is exercise 63, which has to do with the concept of functional derivative that I introduced in the last lecture, and also its relation to conservation laws. So as you will see, some of the calculations are similar to those we did in exercises in the first term when we discussed conservation laws, and some are related to the new material. So let's start with part one. So we want to find the function small f of u, the field, its x derivative and its second x derivative, and the functional capital F of the field u, which is given by the integral of this function small f over x. So I remind you that the functional takes a function u of x and in principle t, but we're not interested in the t dependence here, and outputs a number, the result of this integral. So, and we want to determine this functional f such that the equation that we see here, so ut is the partial derivative with respect to x of the functional derivative of the functional above with respect to u, is the same as the fifth order KdV equation that is written down here. Okay, so how can we approach this problem? So we want to write down ut as a function as a total x derivative. So we want to express this quantity here as minus the partial derivative with respect to x of a function derivative of a functional f of u that we want to determine. Okay, so we can do it in two steps. So first we want to express this quantity, which is underlined in gray, as the x derivative of something. So 30u squared ux is a total x derivative. 20ux uxx is also a total x derivative. Uxxxxx is a total x derivative, but 10u uxxx at first sight is not, well, and even at second sight it's just not a total x derivative. So but we can rewrite it as a total x derivative if we do the tricks that we do when we integrate by parts. Okay, let's write down the expression underlined in gray. The first, second, and fourth term are already total x derivatives, but the third one is not. So to express it as a total x derivative, we can do the trick that we do when we integrate by parts. So we write it down as a total x derivative plus an extra term. So let's do that. So first I'll copy the other term. So we have 30u squared ux plus 20 ux uxx. And then I'm going to write 10u times the third derivative of u as 10 u uxx, all differentiated with respect to x, plus, well, actually minus 10 ux uxx. So I have to subtract the term where the derivative acts on u. Okay, and then we have the last term, which we had above, which is the fifth derivative of u. So now I can group together the term 20 ux uxx with the minus 10 ux uxx that I obtained by this trick here of writing things up to a total x derivative. And so we have 30u squared ux, that's equal to the x derivative of 10u cubed. Then we have 20 minus 10, that's 10 ux uxx, that's equal to plus 5 ux squared x derivative. Then we have plus 10 uxx x derivative, and the last term is just the x derivative of the fourth x derivative of u. So in total, we can write this down as the x derivative of 10u cubed plus 5ux squared plus 10uxx plus uxxxx plus in principle a constant. Let me write minus c for c integration constant. Which upon taking the x derivative gives 0. Okay, so this expression here, we should identify, if we look at the equation above and this one here, as minus the x derivative of the functional derivative of capital F of u with respect to u. Okay, so from this we learn that delta, the functional derivative of capital F with respect to u is equal to minus the expression in brackets, so minus 10u cubed plus 5ux squared plus 10u times uxx plus uxxxx plus the integration constant c. So we're halfway through the computation, so we've determined the functional derivative of capital F with respect to u. But now we want to actually find the functional capital F of u from this functional derivative. And so we can use the formula for the functional derivative of a functional f, which is given by this expression here as an integral of a function small f that we computed in the last lecture. So this should be identified with the partial of f with respect to u minus partial derivative with respect to x of partial of f with respect to ux plus second derivative with respect to x squared of the partial derivative of f with respect of uxx. So now essentially we need to determine the function small f of uxx. And so what we need to do is to express the quantity here as the sum of a second derivative with respect to x plus first derivative with respect to x plus another function. So let's do that. So let me call this equation here star. So now we can rewrite equation star as functional derivative of capital F with respect to u. So let's start from the highest derivative. So we want a second derivative with respect to x. So clearly the last term here, which is u xxxx, is a fourth x derivative. So that's also the second derivative of the second derivative. And I forgot a minus sign. Okay, so next we want to write some of the other terms as a first derivative possibly. And one way to do that is to recognize that we have 10u uxx. And we can again write this down as a total x derivative plus something else, essentially by doing the trick that we do when we integrate by parts. So we can write down minus 10u uxx as minus 10u ux differentiated with respect to x. But then we need to add back plus 10 ux squared. And that's because when the derivative with respect to x acts on u in the expression 10u ux, we have an extra term that we need to cancel out. Okay, and then I have the missing terms here in equation star, so I need to subtract 5ux squared, 10u cubed, and add c. Okay, so this tells us that so we would like the function small f of u ux uxxx to be such that the partial derivative of small f with respect to u xx, that's the expression here that is differentiated twice, it should be equal to minus u xx. Then, so that takes into account that term. So next we have the first derivative term here. Well, let me indicate it differently. So from comparing the two terms which are underlined with the wiggle line, we obtain that the function, the partial derivative of f with respect to ux should be equal to 10 ux. And finally, we have the terms which are not underlined. That tells us that the partial of f with respect to u should be equal to 10 minus 5, that's 5 ux squared, minus 10 u cubed plus c. Okay, so a priori, so these are three equations. It's not obvious that we can solve them in terms of a single function f of u, ux, uxx, but hopefully we can, because that's the exercise. So let's just integrate the last equation first, and then we'll check whether the first and second equations are also satisfied. So if we integrate the last equation, partial derivative of f with respect to u is given by this expression here, then we obtain that f of u, ux, uxx is given by, so when we integrate with respect to u, 5 ux squared u, so here we're treating u, ux, uxx as independent variables. So we have 5 ux squared u. And then the next term, we have to integrate u cubed. That gives u to the fourth divided by 4. So that's minus 5 over 2. So 10 over 4 is 5 over 2 u to the fourth. And finally, plus cu plus an integration constant, which is actually constant with respect to u, but could be a function of ux and uxx. So let's call it g of ux, uxx. So that's integration constant, which in this case is actually a function. Okay, so now let's compare the other two with the other two equations. So let's first look at the partial of f with respect to ux. So here we get, from the expression that we just wrote, we get 10 ux times u. And then the second and the third term do not depend on ux. And then we have partial of g with respect to ux. So now if I compare this expression with the expression underlined by the weekly line above, we see that the partial derivative of g with respect to ux has to vanish. So g does not depend on ux. We can still depend on uxx. So to do that, let's compare with the derivative with respect to uxx. So here, the dependence on uxx is just through g. So that's just derivative of g with respect of uxx. And now if I compare with the expression above, this must be equal to minus uxx. And so g is equal to minus a half uxx squared. Okay, so and in principle now we still have an integration constant. Let me call it d. So now I'm gonna do something that I shouldn't do, but you can see what I'm doing on the screen. So I'm gonna replace g here just by minus uxx minus a half uxx squared plus d. okay, where d is still an integration constant. Now, normally we would, so for equation of KdV type, we would assume that u and all its special derivatives go to 0 at infinity, and we would like the integral here to converge. But we see here that the integrand, when uxx tend to 0, the integral tends to d. Okay, so if we want the integral to converge using the usual, the integral that defines f here, to converge using the standard boundary conditions, so using boundary conditions that uxx tends to 0 as x goes to plus or minus infinity. So we need to require that d is 0 to ensure that the integral capital F of u, which is integral over x of small f, converges. Okay, so d will be equal to 0. And also, in fact, the question only asks us to find a functional capital F of u such that these two equations are the same. And we found infinitely many such functionals because we have this undetermined parameter c, so we're free to take c equal to 0. If we wish, which I will do. Okay, so eventually I will also set this to 0. All right, so this answers part 1 of the problem. So next, there are 2 more parts in this problem. So part 2, I think I will skip it. So just because it's a little long and tedious, but you can see the steps of the calculations in the notes for the problems class that I posted on Duo. So the question, part 2 of the question is as follows. So we want to show that the functional that we just computed is a conserved quantity if u evolves according to the standard third order KdV equation, which I remind you is ut plus 6 ux plus uxxx is equal to 0. Okay, so this is a type of exercise that we did quite a few times during the first term when we studied conservation laws. And so I'll let you do this as an exercise because this is really completely analogous. So once again, so the logic there is that you want to show that, I'm just gonna tell you the logic here. So we need to show that the continuity equation d rho by dt plus dj by dx is 0 for rho, say, equal to the function f, which we determined above. So that would be minus a half uxx squared plus 5 ux squared minus 5 over 2. So that's 5 over 2 u to the 4. That's the charge density. So I want the continuity equation to hold for this charge density and density J to be determined such that has the same values at plus and minus infinity. All right, so instead, let's move on to part 3. So in part 3, we're asked to show that the integral of u over space is a conserved quantity if u evolves according to the fifth order KdV equation that we obtained in part 1. One way here to approach this question is to do computations, again, similarly to what you would have done in the previous part. So you would compute the partial derivatives. Now the charge density would be u, and you would like to determine a continuity equation for an appropriate current J. So you could do the exercise from scratch. That's definitely what we did when we did this exercise for the KdV equation. But actually, there is no need to do that because we have done all the computations that were necessary in part 1. Because indeed, remember part 1. So recall part 1. So we found that this equation here is equivalent to ut being equal to partial derivative with respect to x of the functional derivative of f of u with respect to u. Okay. For again, functional f of u, which is equal to integral dx from minus to plus infinity of small f, which is minus a half uxx squared plus 5 ux squared minus 5 over 2 u to the fourth, and then again I set c to 0. Okay, so the functional derivative of capital F with respect to u is precisely the current that we computed in part 1. And the current, when we set c equal to 0, so partial derivative of f with respect to u, when we set c equal to 0 was equal to minus 10 u cubed plus 5 ux squared plus 10 uxx plus fourth derivative, and then we had plus c, but we set c to 0. So now we can identify this with minus the current in the continuity equation. So, and then u would be equal to rho. So then the equation above is just d rho by dt plus dj by dx is equal to 0. So we only need to check that the current J takes the same values at plus and minus infinity. So, but again, we use the boundary conditions where u and all its special derivatives go to 0. So J tends to 0 as x goes to plus or minus infinity. So it takes the same values at plus or minus infinity. And therefore, we have the two conditions that we need. So first, we have the continuity equation here. And secondly, we have the boundary conditions here. So that tells us that the integral over x of rho, which is equal to u, does not depend on time. So it's a conserved quantity. Okay, so there was no need to do any further computation. So the important point here to realize with this exercise is that equations of the type written here are always written in the form of a conservation law. And in particular, we saw in the lecture that all the equations in the KdV hierarchy are written in this way. And so there is always a conservation law that is manifest for free, but in fact, there are infinitely many more conservation laws. Okay, so part 3, in fact, was much easier than part 2 that I decided to skip because we really didn't need any further calculations. Okay, so next exercise is actually a little new. So this is exercise 64. It's an exercise which would have made sense to do in chapter 12 that I don't have time to cover in the lectures because of the strike. But in fact, I decided to do this exercise here in the problems class because, as you see, everything that we need to know to solve this kind of exercises has to do with the Lax equation that we have already studied. So this is just an exercise on the Lax equation in a simpler context than partial differential equations like the KdV equation that we focused in the rest of the course. So just to give a bit more context, let's look at the problem set where I wrote a little bit more background information. And if you're interested, you can read more in the lecture notes for chapter 12, but that's not really needed. Okay, so here is the context. So we've seen how the Lax equation appears naturally in the context of the KdV equation, but in fact, it appears naturally also in much simpler systems, which are just classical systems, which, for instance, could describe several point particles, which may interact with a potential or have interact among themselves. So in particular, we could consider a system with a so-called finite number of degrees of freedom in classical mechanics. So the degrees of freedom would be some finite number of coordinates qi, which are function of time t, and the momenta pi, which are also function of t. And let's say there are n coordinates, then there are always n so-called conjugate momenta. So this should be contrasted with the partial differential equations or field equations that we studied, like KdV, because there we have, that's the footnote here. So there we have a field u, which is a function of x and t. So we can think of it as a system with infinitely many degrees of freedom, because at fixed time t, u can take different values at each different position x, and there are infinitely many different positions x along the real line, so that has infinitely many degrees of freedom. So now we just have a finite number n of degrees of freedom, n coordinates, and n momenta. So this is a much simpler system. And the type evolution in this type of classical system is governed by Hamilton's equation, which are given here in question 12.1. In terms of partial derivative of a function called the Hamiltonian, which is a function of the coordinates q and the momenta p. And this Hamiltonian, in fact, has an interpretation of being the total energy of the system, so it's independent of time. And as we've seen also briefly in the first term, at some point when we did an analogy with classical mechanics, I reminded you, or I told you, that classical systems might have a Hamiltonian, which is the total energy of the system, and it's given by a sum of a kinetic energy T of P and the potential energy V of Q. So it would take this form like here, because the kinetic energy, well, for most systems is sum of the square of the momenta divided by 2 times the mass. I'm setting the mass to 1 here for simplicity. Okay, so for systems of this type, then Hamilton's equation that I wrote up here take a simple form. So let's look at the equation for Q dot. So dots are derivative with respect to t. So Q dot is partial derivative of the Hamiltonian with respect to p, but the partial derivative of Hamiltonian with respect to p is just p. So Q dot is equal to p, so the momentum is simply the velocity. If you restore the mass, it would be the mass times the velocity. And then the other Hamilton's equation that we have here is P dot. Now it's nothing but Q double dot. So second derivative of Q is minus partial of the Hamiltonian with respect to Q, which is if we use Hamiltonian in equation 12.2, is just minus the derivative of V, the potential, with respect to Q. So this is nothing but Newton's law, force, which is minus the derivative of the potential with respect to Q, is mass times acceleration. So here mass is 1 and acceleration is Q, double dot. Okay, so this was all the detour that we needed. So now the point is that some of these classical systems are actually integrable. And this is the case when these equations of motion, either written in Hamilton form in 12.1 or Newton's form that we just saw, are equivalent to the Lux equation for a Lux pair L and M, which now are not differential operators as was the case for the KdV equation, but just matrices with as many, with the size equal to the number of degrees of freedom. So the Lux equation for us will be equations for two functions L and M, which are matrices of size n. Okay, and this can depend on time, and the Lux equation involves the time derivative of L. That's equal to the commutator of M and L. Okay, so now let's go to the exercise, which is you can read here, but I've also written here in the notes. So now we're considering a simple classical system of that type. So don't worry if you didn't get all the points. So you see that everything you need to know is explained here in the exercise. So we take n equal to 3, so 3 degrees of freedom, and the coordinates are qi, which are identified with qi plus 3. So there are essentially 3 coordinates which are periodically identified, and the same for the momenta. So qi and pi, which are equivalent to qi plus 3 and pi plus 3, are the coordinate and momenta of a classical Hamiltonian system. And then we have a pair of Lux matrices L and M, which should be 3 by 3 matrices because we have 3 degrees of freedom, and are given as here. So as usual, we can take L to be Hermitian and M to be anti-Hermitian. And in fact, here everything is real. So L will be Hermitian and real, so symmetric, and M will be anti-Hermitian and real, so anti-symmetric. Okay, which you can see from the expression that they are. So L is symmetric and M is anti-symmetric. So L depends on the momenta P1, P2, and P3. And we're told that, as in the case where we would get Newton's equation, P dot I is equal to Qi, the positions, whereas Bi, which appear both in L and in M, so in both of the matrices in the Lux pair, are given by exponentials of a constant C times the difference of the coordinates of 2 neighboring particles, Qi minus Qi plus 1, for some real constant C. So this is the setup. And now we're asked to use the Lux equation, which says that the time derivative of L plus the commutator of L and M is 0, to find the constant C, and also to obtain equations of motion for this coordinates Qi of the form here, which are essentially Newton's equation for some functions that we can think of as forces, Fi of Q, that we need to determine. Okay, so this is the exercise. So we need to, so it might sound scary, but we don't need to do that much. So first of all, we want to write the Lux equation in terms of the 2 matrices L and M, which appear in the Lux pair. So let's compute first L dot and then the commutator of L and M. So L dot is easy to compute. So I just take L and I write dots on top of everything. So I have the derivatives, dots are time derivatives, again, of the momenta along the diagonal, and the time derivatives of B I, which are functions of the coordinates of diagonal. So B1 dot, B2 dot, B3 dot, B1 dot, B2 dot, B3 dot. Okay, so then this, by the Lax equation, should be equal to a commutator of M with L. So let's compute that commutator. So now we have, well, let's compute ML and LM separately. So for M times L, I have, so in the first entry, I have B1 squared minus B3 squared. So then entry 1, 2 is 0 times B1. I have B1 times B2, B1 times P2, sorry, minus B3 times B2. And for the last one, I have B1, B2. Minus B3, P3. Okay, so then for the entry 2, 1, I have, so second line, second row of M, first column of L. So that's minus B1, P1. Plus B2, B3. Then I have minus B1 squared plus B2 squared. And finally, I have minus B1, B3 plus B2, P3. Okay, so next, third row of M times first column of L, I get B3, P1 minus B2, B1. So I'm gonna write it as minus B1, B2. And third and second, I get B3, B1 minus B2, P2. And then I have B3 squared minus B2 squared. So that was M times L. So next we need to compute L times M. And then we'll take the difference. Okay, I think I might need space. So okay, for L times M, I get entry 1, 1 is B1 squared minus B3 squared. Entry 1, 2 is P1, B1. Oops. P1, B1 minus B2, B3. And entry 1, 3 is minus P1, B3 plus B1, B2. Okay, so then entry 2, 1, I have minus P2, B1 plus B2, B3. Entry 2, 2 is B1 squared minus B2 squared. Sorry, just see, I made a mistake when I computed the entry 1, 1 of LM. That was P1 times 0 minus B1 times B1 plus B3 squared. So I had to correct the signs. Okay, so now back to entry 2, 3 of L times M. So that's minus B1, B3 plus B2, B2. Finally, the last row of L, so I get minus B1, B2 plus B3, 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 B1 minus B2, P3 and minus B3 squared plus B2 squared. Okay, hopefully I didn't make any mistakes. So let's compute the commutator next. So let's compute commutator of ML. That's just the difference of these two equations. And this should come out as a symmetric matrix because it's supposed to be equal to L dot and L is symmetric. So that will be a consistency check. So for entry 1, 1, I get B1 squared minus B3 squared plus the same. So I get 2 B1 squared minus B3 squared. Okay, let's continue with the entries on the diagonal. So next one, I get 2 times B2 squared minus B1 squared, and entry 3, 3 is 2 times B3 squared minus B2 squared. Okay, so we see that there is some nice cyclic structure, which agrees with the fact that Qi and Pi were cyclically or periodically identified. So that looks good. Now let's look at the terms of the diagonal. So let's first look at the entry 2, 1. And we see that nicely the terms that involves the product of two B's cancel out when we take the difference. So we just have B1 times P2 minus P1. Good. So let's check 2, 1, which hopefully should give us the same result because we expect the matrix to be symmetric. So for 2, 1, get again the terms involving two B's cancel out, and we get B1 times P2 minus P1. That's good. So okay, now entry 2, 3, we get B2 times P3 minus P2. And for 3, 2, we do indeed get the same result. So we see again some cyclic structure. So now let's look at entry 1, 3 times P1 minus P3 in entry 1, 3, and in entry 3, 1, I have the same. Okay, good. Right, so now we want to identify this commutator here with L dot as computed up there. So they're identified by the Lux equation. And when we do that, we'll determine what P1 dot is, but we are told that Pi dot is equal to Qi. So that's what we'll see from the equations in the diagonal. Sorry, this I think is completely wrong. So what I wanted to write is that Pi is Qi dot. I see there is a typo also in the notes that I posted on Duo. Apologies. I will correct that. So to summarize, we want to now equate L dot computed here with the commutator of M and L computed there. That's what the Lax equation tells us, that these two quantities are the same. So, and when we do that, we want to determine the constant C, and also to obtain equations of motion for Q that are of the type of Newton's law, acceleration equal to a force. So we'll get to Newton's law when we look at the Lax equation in terms of a diagonal element. So the diagonal elements of L dot are Pi dot, which is Qi double dot. And those are equal to some functions of B's, which are in turn functions of Q. So we'll obtain Newton's equation from the diagonal elements, but we first want to determine the constant C. So for that, let's look at the terms which are off diagonal. So let's look, for instance, at entries. I plus 1 I, again, where say I is defined modulo 3. And we could also look at I plus 1 because the matrices are symmetric. That would be the same. So, okay, so what are these equations like? So for, let's look at entry I plus 1 I of L dot. That's just equal to Bi dot. Whereas entry I plus 1 I of commutator of ML, as you see, let's for instance look at 1, 2. That's equal to Bi times Pi plus 1 minus Pi. So now if you look at, I chose I equal to 1, but if you look at I equal to 2 and 3, you will see the same structure. Okay, so now we can rewrite this equation by taking Bi to the denominator in the left-hand side. And so this is nothing but time derivative of the logarithm of Bi equal to Pi plus 1 minus Pi. And now we plug in the expression for B that is written here. So let's plug in Bi equal to exponential of C times Qi minus Qi plus 1. So, and also we know that Q dot I is equal to Pi. So, okay, for the log of Pi is just this, the exponent, and then we need to take the time derivative, so that's C. So C is a constant, and then we have time derivative of Qi, so Q dot I, that's equal to Pi, minus Q dot I plus 1, which is equal to I plus 1. So that's the left-hand side here of this equation. That should be equal to the right-hand side, which is Pi plus 1 minus Pi. So we learn that C is equal to minus 1. Okay, so we've determined the constant C. And now finally we have to look at the diagonal terms to obtain equations of motion in this form here, which is just Newton's law. So let me do that in the next page. So next we look at entries II, so diagonal entries. So let's go back. So, oops, sorry. So the Lax equation is that L dot is equal to commutator of ML. So the diagonal entries of L dot are P dot I. So we get P dot I. And this is equal to the diagonal entries of commutator of L times M, which we see are equal to 2 times BI squared minus BI plus 1 squared. Sorry, minus BI minus 1 squared. So for instance, let's look at entry 22. We have 2b2 squared minus b1 squared. Entry 33, we have 2b3 squared minus b2 squared. And entry 11, which is the same as 4, we get 2, if you want, b4 squared, which is b1 squared minus b3 squared. So what we find is that this is, the right-hand side is just 2 times bi squared minus bi minus 1. Sorry, the square is for b. And then we plug in again pi dot equal to qi, and bi was exponential of c, which is minus 1, times qi minus qi plus 1. So that's qi plus 1 minus qi. So what you obtain is that the left-hand side is q double dot I, so that's acceleration. And on the right-hand side, we'll get the force Fi. So that's 2 times bi squared, so that's exponential of 2 qi plus 1 minus qi minus the square of bi minus 1. So that's exponential of 2 qi minus qi minus 1, which we identify with the force Fi of q.